Hello, my name is Francisco Weber. I'm a co-founder of CEPT Systems, a startup company based in Vienna. CEPT stands for Cortical Engine for Processing Text. Based on the results of a scientific project funded by the Austrian government, we have developed a unique type of search engine technology that is engineered using processing methods similar to the human cortex. We believe that the discovery of the CEPT algorithms will become a game changer in many natural language arenas of business computing. The CEPT-Retina algorithm allows computers to understand written language by generating semantic fingerprints of any piece of written text. The semantic fingerprints are capturing the inner meaning of a word, sentence, paragraph or document. Using the CEPT-Retina, the computer can compare, add or subtract concepts. By processing word fingerprints, the system can automatically disambiguate homonyms or automatically expand keywords provided by the user with context terms. The use of paragraph fingerprints helps to scan text for plagiarism or spot forensic evidences. The generation of document fingerprints enables to search through vast amounts of text material, without suffering the limitations of traditional keyword-based approaches. The fingerprints are generated by applying the CEPT-Retina to arbitrary text elements. The inventive step of the CEPT-Retina consists in converting symbolic into discrete representations of language, maintaining its full semantic richness. The retina is generated fully automatically, based on a carefully crafted training set of reference material. The retina can capture any specific language in the same way as human is trained to a specific literacy. By teaching the retina domain jargon or some professional terminology, the semantic resolution of the system can be increased, while implicitly reducing ambiguities and noise usually associated with natural language processing. The algorithm that generates the CEPT-Retina is fully independent of the actual language used. The CEPT system can therefore be used with any language. Allowing the full set of similarity, disambiguation and arithmetic functions. Future development of the retina will allow cross-language search between any possible language pair. In theory, the CEPT approach will also be helpful to improve existing machine translation systems. In order to illustrate this, I want to show you how the CEPT-Retina can be used to tackle an old artificial intelligence challenge that is easy to do even by young children, but has been shown to be difficult for computers. Discriminate between cats and dogs. A picture of cats or dogs represents a good example of a traditional method for capturing semantic information. In many cases, analyzing the shapes and image properties might work. The associated computation is intensive, but it might be feasible for some applications. The words cat and dog are symbolic representations of the entities cats and dogs. To give actual meaning to these symbols, we need a dictionary that specifies the meaning. As we are unable to correctly interpret the symbolic representations on themselves, this approach works fine as long as the corresponding dictionaries are available and are kept up to date. But unfortunately, the use of dictionaries is prohibitive in many real-world applications due to high creation and maintenance costs. The CEPT-Retina transforms the symbol for cat into its semantic fingerprint shown here in red. The same for dog, shown in blue. In the middle, you can see both fingerprints in an overlay, showing common points rendered in black. They correspond to the semantic intersection. Distance measures can easily be computed for any sets of words, allowing to express their semantic relatedness in a numerical description. The representation of every word is realized by means of 16,000 variables called semantic features that show a similar topology for similar meanings. The overlay of two word representations enable direct, even visual comparison of semantic relatedness. The semantic distance is processed in a quantitative way by counting the numbers of shared points. But it's also a qualitative measure by identifying which points in the 2D space are actually shared. Traditional natural language processing techniques only process a very limited number of quantitative features, typically based on the document and collection frequencies of an indexed term. We call this encoding of semantic features semantic fingerprinting. Let me illustrate this with some examples. In this example, you see the screen of our Retina dictionary viewer. This tool allows you to compare the semantic fingerprints of two words. This is just meant as a visualization. To use the functionalities, you don't need to see the bitmap representations. In this example, we see on the left side in red the representation of the word apple, and on the right side in blue the word iPhone. The gray boxes represent cluster areas of higher densities that the system has detected. In the center field, you see the overlay of the two. Black dots are areas where the two fingerprints match. Please note the two clusters of matching dots. These shared dots tell the system that there is a semantic relationship between the word apple and the word iPhone. In a second step, we compare the same word apple to the word fruit. The blue pattern changes and we see other matching overlay areas. This means that the system recognized semantic relatedness in three matching areas. But the nature of this relation is different from the previous one. The system has found a second meaning of the word apple. In the third step, we compare apple to the word Beatles. As the Beatles published with Apple Records, the system spots a third area of overlay representing a third context for Apple. In contrast, if we compare the word iPhone and fruit, we see practically no overlap. The previously described capability of detecting different meanings of a word are exposed with the context disambiguation tool. For every submitted term, the system finds the best matching context terms, like here for the term apple. The right side shows a list of subcontexts that are named after their first term. By clicking on a subcontext item, the list on the left side changes, now only showing the list of context terms in the selected subcontext. There is a Apple computer context. Next, we see the Apple records context, followed by the Apple fruit context, and so on. The input is not limited to terms. The Retina is capable of evaluating meaning-based expressions formulated as arithmetic operations. Here, the context of the word computer is subtracted from the context of the word apple. As a result, the context computer disappears from the list of subcontexts on the right. After subtracting even further, the contexts of record, of food, and version, all subcontexts of the word apple have been identified. By creating fingerprints from documents of a collection, the CEPT system can act as a similarity engine. The degree of similarity depends purely on the meaning and not on the occurrence of specific keywords. The first simple prototype allows just plain searching through 4 million Wikipedia documents. If we start a search session just using one keyword like Concord, we get all sorts of results that are related. We get, for example, a football club named Concord. In short singleton queries, the generated fingerprint shows no hints in which context they could be meant. There are documents about aeronautical museums, air shows, and aviation engineers. By selecting the More Like This function, we can transfer the selected document text about Archibald Russell into the query box. The system now generates a fingerprint out of this query document, providing a much richer context. As a result, we now get documents about aviation engineers, their companies and their airplanes, all similar in some aspects to the biography of Archibald Russell. The CEPT technology can be applied on several different levels of text analysis. It can process words for query expansion, annotation, and disambiguation functions. It can operate on documents or document sections to realize semantic search systems. It can be applied to user-provided text that is used as an example for the user's interest. This semantic user profile can individually rank result sets to best match the individual information needs of users. These different fingerprint items can be processed using three basic functions. Using the expression engine, computers can now freely combine and compute concepts to perform any meaning-based task. The highly performant similarity engine provides efficient search and compare functions on any text content. Whenever a single piece of text could be interpreted in multiple ways, the disambiguation engine helps to select the right context. The CEPT-Retina is accessible through an API. The provided functionalities can be consumed as web services and can be incorporated into any existing IT infrastructure. The Retina is constantly improved, offering new enhanced functionalities over time. For easy onboarding, developers can register at no cost and begin their exploration of this new technology right now. After registering to the free beta program, users can access the interactive API documentation, getting the full information on every method. They can try out every existing parameter immediately, as well as analyze easily every result. If you want to find out why Jaguar minus Porsche equals Panther, then please visit the demos on our website or contact me by email.